particle is projected with a speed of 98 meters per second at an angle alpha to the horizontal. The range of the particle is 940.8 meters. Find the two values of alpha. We can get the x components of the initial velocity. 98 cos alpha gives us ux, 98 sin alpha gives us uy. The y position of the particle is given by the formula s equals ut plus a half at squared, but applied in the y direction. So this is a formula from linear motion with constant acceleration. The constant acceleration ay is minus 9.81 because we're taking upwards to be positive. Now, when the particle strikes the ground, we know that sy is 0. We could actually just call this y, if you like. It's just the letter s is normally used for position. So, putting 0 in here, we have 0 equals uy, which is 98 sine alpha times t. T here will be the time taken for the particle to go from here, to the point where sy is 0. So t is actually the time of flight. A half of ay is a half of minus 9.81, which is minus 4.9. We can solve this for t, factorize t out of it. We get one solution, which is t equals 0. The other solution we get will be 98 sine alpha divided by 4.9. So we've seen this before. This is a quadratic. We can factorize t out, so it's t into 98 sine alpha minus 4.9 times t. Put each factor equal to 0. We get a trivial solution at t equals 0, sy equals 0, of course. But this other value of t also gives us sy equals 0. So this time here is the time of flight. 98 divided by 4.9 is 20. Of course, we can find the x position of the particle. Just apply the formula s equals ut plus a half at squared in the x direction, but ax is 0. The acceleration of the particle is entirely in the y direction, as I've explained several times before. So ax is 0 because there's no force in the horizontal direction. We're ignoring a resistance. No force in the x direction implies that the x component of the acceleration is 0. That comes from Newton's second law. Explained all that. So when the particle hits here, the x position is 940.8. The x component of the initial velocity is 98 cos alpha. T is the time taken for the particle to go from here to here, which we now know is 20 sine alpha. So we multiply ux by the time of flight. So we need to solve this equation. Multiplying 98 by 20, we get 1960. And what about cos alpha, sine alpha? Well, we can use an identity to take care of that. So just to remind you, 2 cos alpha sine alpha can be written as sine 2 alpha. This makes it much easier to solve this. Well, it's the only way I know actually for solving this trigonometric equation. We want to write these two trig functions as a single trig function. So this is the identity that you can look up. So cos alpha sine alpha is a half sine 2 alpha. So we have 1960 divided by 2. We eventually get sine 2 alpha equals 0.96. So 2 alpha equals inverse sine of 0.96. So I'll get alpha in degrees. So in degrees we get 73.74. But that's not the only answer. We know from trigonometry that the coordinates of a point on a unit circle, which is a circle with a radius of 1, are cos theta, sine theta, where theta is measured anti-clockwise from the positive x-axis. So if theta is 73.74, well, it's called 2 alpha here, then the coordinates of this point are cos 73.74, sine 73.74. So it's the y value that we're interested in. The sine of 73.74 is 0.96. So this here, the y value of this point is 0.96. But that's not the only angle whose sine is 0.96. This is not the only point on the unit circle whose y value is plus 0.96. The other point is this point here. This point is got by reflecting this point directly through. So we get a point whose coordinates are cos of this angle here, sine of this angle. So what is this angle? Well, it's 180 minus 73.74. So to two decimal places, we get 106.26. So we see that the sine of 106.26 is also 0.96. So there are two values for the angle, which is 2 alpha. It can either be 73.74 or it can be 106.26. So that means there are two values for the launch angle. We divide this by 2, we get 36.87. We divide the other angle by 2, we get 53.13 degrees. So we have found that for a launch speed of 98 meters per second, the two angles that give a range of 940.8 meters are 36.87 degrees or 53.13 degrees. In part 2 we want to find the difference between the two times of flight for each launch angle. So the time of flight is given by 20 sine alpha, so we plug each launch angle in turn into this. So when we plug in 36.87, we get a time of flight of 12 seconds. That's the time taken for the particle to go from here to here if the angle is 36.87, and for the other angle 53.13 we get a time of flight of 16 seconds. The difference in the times is 16 minus 12, which is 4 seconds. As an aside, note that these two angles add up to 90 degrees, and that kind of makes sense because to get this second angle we multiplied this by 2. We could multiply this by 2 to get 73.74, then we subtracted from 180 to get 106.26, then we divided by 2 to get back to this. But multiplying by 2, subtracting 180 and dividing by 2 is equivalent to actually seeing that the two angles add up to 90 degrees, if you think about it. So, for a given initial speed, the two launch angles that give a certain range sum to 90 degrees. Let's just see an animation of that. Let's suppose that the launch speed is 51 meters per second. We can make the launch speed anything we like, but let's suppose that the launch angle is 28 degrees. Let's launch this particle. We can see that the range is 219.8 meters. Now, let's keep the launch speed at 51 meters per second, but change the launch angle. Remember that if the two launch angles sum to 90 degrees, then the range will be the same for a given speed. So what is 90 minus 28? Well, that's 62. So we'll just change the launch angle to 62 degrees. Now, if we launch the object, the range should be the same. So there it is. It's also 219.8 meters.